working? Okay, perfect. Hi, everyone in person, and hello to everyone online. My name is Kunal Vaishnavi. I'm a software engineer at Microsoft, and today I'll be talking about inference optimization with ONNX Runtime. So let's get into it. I think first thing, a lot of people have a lot of confusion between what ONNX is and what ONNX Runtime is. I thought I'd clarify that right off the bat. ONNX is an open source format that is used to represent your machine learning models as directed acyclic graphs. In your graph, you have a set of inputs, you have a set of outputs, and then a set of graph nodes or operators that are used to execute your model. Within ONNX, there's a primitive set of these operators that are defined.
Is your mic on? Can you check?
This is not on?
Can you check if it's
closer? Is this better? Okay, sorry. Yeah, so you define a primitive set of operators. Sorry, I lost my train of thought. To define a primitive set of operators called standard ops. And if there are any version changes that are made to these standard ops in ONNX, like let's say a new basic operator is added, like short-term Fourier transformation, which is used for signal processing, then it would, there would be a version release update, and we would upgrade what we call as the opset. And then ONNX Runtime, on the other hand, is a cross-platform ML inferencing and training accelerator. It implements all of these standard ONNX ops per execution provider, so per hardware target. And it defines and implements an additional advanced set of operators called contrib ops, which is what today's presentation will kind of be more focused on. And it allows users to write their own operators called custom ops. I'll put my phone down because I keep getting buzzed. Sorry about that. And so you're allowed to write your own operators called custom ops. You, the user, you can then write an implementation for it, for the EP that you're targeting, let's say the CPU EP. You write your implementation, which is called a kernel. You register it with the CPU registry, and then it'll run within ONNX Runtime directly. How do you actually get to ONNX, though? Typically, a lot of developers work in their main AI framework tool. Most common is PyTorch, TensorFlow, sklearn, and a lot more other options. And within each AI framework tool, there's usually some type of convert to ONNX, export to ONNX API. Typically, we focus more on the torch script export, which is torch.onnx.export. And as Yusheng mentioned, we're now working towards the torch dynamo export, torch.onnx.dynamo export, which is in beta at the moment. And there's a lot more community maintained ones as well. So how does that torch script export actually work? Well, you pass your PyTorch model. You pass dummy inputs. The reason you need to pass your dummy inputs is so that when the exporter actually runs, it runs a forward pass through your PyTorch model. Using those dummy inputs, it can then trace which branches are called, which operators are used, and makes basically a recording of all that information. And then from that recording, we're then able to translate that into an ONNX graph. Specify your file path that you want to save the model to, the input and output names for your ONNX model, in the ordered list that you would call them. Like let's say you're calling your forward pass, your input names then called in that order, and then the output names from your PyTorch model, specify those as well. Dynamic axes is used to specify dynamic shapes within your inputs and outputs. Let's say you have an attention mask and it's a 2D shape of batch size, comma sequence length. You don't want your model to only work with a batch size of 1 or a batch size of 2. You want it to work for varying batch sizes, so you would want to specify that in your dynamic axes. Of course, there's the offset number that specifies the offset version to use for the model for all the operators. And then the export modules as functions, I'm going to skip over that for now because we're going to get to that later. But basically, it converts torch NN modules to ONNX functions. And then finally, there's constant folding, which is a way of simplifying the graph. If there's a primitive operation like 1 plus 2 for some reason in the graph, constant folding will just automatically compute that, simplify it to 3, and put that into the ONNX graph for you. On the other hand, the torch dynamo exporter is a much simpler API to use. You pass your PyTorch model, your specific inputs, let's say input 0, input 1, however many there are. If there are keyword-specific inputs, you pass those as well by specifying the input name and then the dummy input. And then within your export options, you just turn on dynamic axes, basically. That returns you a model proto in ONNX, and that's basically your ONNX model already in memory. Then you can choose to manipulate that model proto if you wish, or if you want to just save it on disk, .save will do that for you. So this is an example of what an ONNX model might look like after export. On the left is kind of a screenshot of a snippet of it. And on the right, I've kind of zoomed in on what you see this big red block is. There are a lot of operators just in that red block alone. And the ones that are circled in red, even in the right graph, are if nodes. If nodes are kind of problematic usually because if the if branch is called, then it has to run a separate graph. If the else branch is called, then it runs another separate graph. And those graphs may or may not be separate from the main graph here. So typically we try to, when we export, remove or rewrite our implementation in the original format so that these if nodes go away. And it can be sometimes very simple. As a primitive example, in this case, on the right, you can see what the original code looked like. Oh, it might be hard to see what's in red, but basically it's these 4 are the original lines, and then these 2 are the new lines. And what happened was only these 2 lines were removed. So these were squeeze operators that got removed from the graph. And as you can see, the number of operators that are now there is much less. So once you have your ONNX model, how does it actually run? Well, there's your inputs, there's your outputs, and then there's your operators in between. And when you're running your ONNX model, let's say you're running on a GPU, first your ONNX model gets loaded into high bandwidth memory. So that's typically when you run, like, let's say you're running on an NVIDIA GPU and you type in NVIDIA SMI and your GPU prints out and it says how much memory your GPU contains. That's your high bandwidth memory. Your ONNX model gets loaded into that. Then for each operator that runs, there's a kernel implementation. And the kernel is launched in something called SRAM, static RAM on your GPU. It's a much smaller space, but can do computations much faster. That's why the GPUs can work so quickly. So memory here is defined as the high bandwidth memory, and compute is the SRAM. So once we reach an operator, we have to transfer our inputs from high bandwidth memory to SRAM, do our computations, then save the output of that back into high bandwidth memory. These transfers, though, are can be very time consuming. And so we try to limit the number of transfers that happen in an ONNX model. And so the way we can do that is through something called operator fusion, which simplifies these operators and merges them, let's say F1 and F2, into a merged one called F1, F2. Even if it takes a little bit more compute, the time it takes to switch between SRAM, where the computations are happening, and HBM, high bandwidth memory, where the main model is less, and therefore the model takes less time to actually run. And in addition, we can also improve on the algorithms that are used to implement these fused operators as well. So that's a simple way of doing an optimization. But within ONNX Runtime, it can be done actually internally and externally. And so what I mean by that is as follows. Internally is within the ORT core code. It's part of your package release. There's nothing additional that you need to do. When you load your ONNX model into ORT's inference session class, these optimizations kind of get applied directly. The problem is, though, if you keep reloading your model into an inference session, they're going to keep getting applied over and over, and it's kind of an inefficient way of having an optimized model. You'd rather just have them already applied and just load your model and run it. So to get around that, we added an option in the session options to specify the optimized path, model path, and in there you can specify the path you want the optimized model to be saved at. Once you load the model into your inference session and you specify the list of execution providers or hardware targets that you're looking for, the optimized model will get saved on disk for you. So that's internal optimizations, but those are also limited as well. Every package that gets released isn't necessarily going to be updated, for a little bit of time. And maybe you want the latest optimizations that came out a week ago. What do you do in that scenario? Maybe you want to change the optimizations that are being applied. You don't like it. You want to change it for whatever your scenario might be. That's when the external optimizations come in. In ORT, there's a transformer optimizer script. It's a Python script, and when that's called, it will basically load your ONNX model, try to detect patterns or subgraph patterns in your model, apply these operator fusions, and rewrite the graph into a fused graph, and then that gets saved on disk, and so now it's in a persistent state. And kind of call the optimizer you just do ONNX runtime.transformers.optimizer, specify your input and output, the model architecture type, the number of attention heads in the model's hidden size, and then using the external data format to reduce the size of the actual ONNX model and keeping the weights separate, in case you want to share your ONNX model but without the weights to someone. And so a lot of the common optimizations that we see externally are as follows. Layer norm or simplified layer norm, skip layer norm and skip simplified layer norm. Difference between those two is an additional skip input and output. Rotary embeddings, multi-head attention, group query attention, and a ton more. I mean, the list goes on. And new optimization opportunities keep coming up as new models get released, new architectures, new modifications are made. And so to keep up with that, we have that external optimization script. So I think for today, I'll talk about the first 5. Those are kind of the core ones we have in the latest LLMs. And yeah, let's get into it. So the first one is skip simplified layer norm. The graph on the right you see is what it looks like in ONNX originally. And I've rewritten it here at the top for you. So there's an add, a cast node, a bunch of other nodes, a cast, and a multiply. And the first thing we like to remove are cast nodes because during export, these cast nodes kind of get inserted for protection purposes and accuracy purposes. And what I mean by that is for whatever reason, maybe your input is in float 32, but the exporter doesn't know that. It'll insert a cast node just to be safe to make sure that the input to, say, the POW is guaranteed to be float 32. So the cast is going from float 32 to float 32, which is essentially a pointless operation. So we like to remove these cast nodes firstly. Then the graph gets simplified a little bit. And then we try to look at these operations and see if there's a theme going on, a mathematical operation that we can kind of fuse them all into. And in this case, you can actually fuse all of these into something called simplified layer norm. Simplified layer norm is, I'll show it in the next slide what it's defined as, but you can actually fuse this as well, add and simplified layer norm into skip simplified layer norm. And so now the graph has been taken from 10 nodes to just 1. And we can write a more optimized implementation of skip simplified layer norm accordingly. Now you might be wondering, why does this work? And we're going to get into the math and the details. But the first thing I want to show is what the skip simplified layer norm operator actually looks like, and compare it to the original graph to show that it doesn't miss any information. So we have here attributes, inputs, and outputs. So the epsilon input is taken, or the epsilon value is taken from the add. The 2 inputs here are taken from the 2 inputs to the add, and the add's output, which is the skip output here, and then this output going to that cast is saved here. And then the layer norm's weight is saved in that mul, so that's stored here, and the output from that mul is also stored here in the output. And why does this work mathematically? Well, it's actually following something called the root mean squared norm. So let's first break that into 2 parts. First is the root mean square. As the name kind of hints, it's the root of the mean of the square of your input. So if you look here, you have the POW operator. Let's say your input is X. It's a tensor of however many elements. The POW operator will then take each element in that tensor and square it. And if we look here, it says, kind of hard to see, but it says y equals 2. So that corresponds to the squaring that's happening here. Then there's the mean. So the mean is defined as the sum of all elements over the number of elements. And reduced mean is basically saying, do the mean over a specific axis, because tensors can be of multiple dimensions. So just do it over a specific axis. The add is so that when we take our square root, there might be a scenario, it's very rare, but there might be a scenario where the mean is computed as 0. Then you have to take the square root of 0, and that's going to cause issues in your computer sometimes. So to avoid that, we add an infinitesimally small value, which we call the epsilon, just to make sure that when we take the square root, it's a non-zero value. And then after that is the square root operator, which is when we take the actual square root. and that gets our root mean square. So now when we go to the root mean squared norm equation, we can see the root mean square is here. Then there's the divide, and it says a equals 1 here. So we have 1 divided by the root mean square value we just calculated. So that's one term. And then the second term is our input x in this mul as well. And if you remember from the previous slide, we said that if the cast is removed, then the adds input is going to go directly to the POW. It'll actually also go directly to this mul. And so that's why that operation kind of happens smoothly. And then there's the multiply by an extra weight vector g. RMS norm is basically a way of normalizing your values and then scaling those values by some factor. So when you do a normalization, if you've taken any basic statistics class, you basically take your input, you subtract the mean, and you divide by your standard deviation. Yeah, and then in this case, the simplify just means we don't do any subtraction of the mean. So that's why in this equation here, we don't do x minus some value. And if you look at this equation here, there's 2 ways of writing it, right? There's the x divided by root mean squared times g. Then there's the x times 1 over root mean squared times g. Both are equivalent mathematically, but in our graph, they may be represented differently. So we have to be able to handle these different scenarios. And there are other cases like maybe in our add input, the epsilon is input 0 versus input 1. Maybe in our POW, the inputs might be switched. In some cases, there might be different graphs, like maybe the div is not there, and we go directly from the square root to the multiply. Sorry, we do the div instead of the multiply. That's what I meant. And it goes x divided by root mean squared rather than x times that. So there's different graph patterns, and you have to be able to pattern match against all these. So that's what, it's kind of hard to see. That's what this code is doing here, is kind of being shown. This is basically what we're writing in our actual Fusion code to pattern match against these different cases. So when we pattern match, we take our end node, and then we match it against a series of parent nodes. So we specify their node names, like mul, div, square root, add, and the actual indices that we're trying to go up in the graph by, because nodes can have multiple inputs and outputs. So the indices are there to help us specify which exact path we're looking for. And this helps us handle different scenarios if there's different pattern matchings that may show up from graph to graph. Another optimization is the rotary embeddings. Rotary embeddings, I've simplified the equation here greatly, but at a high level, it's basically you take your input, you multiply it by something called the cosine cache. It's a pre-computed cache, and it has a complicated equation, so I didn't bother putting it in. But it's multiplied by some pre-computed cache, and then you add this extra term, which is rotate your input tensor halfway, and then multiply it by a similar cache called the sine cache. And up above here is a picture of what that subgraph looks like. So you can see that the equation may look simple, but the actual calculation of it is a lot of nodes. And as you can imagine, pattern matching against this might be exhausting. Pattern matching against variance of this might be exhausting. So how do we handle this? Well, this is when we look at our exporter tool. So we looked at the torch script export, and we found this export modules as function flag, so the one that I glossed over previously. And what it does is it rewrites all these torch NN modules as ONNX functions. ONNX functions are basically a way of saying, here's my inputs, here's my outputs. I don't want to bother about its implementation. It's great that you have it recorded, but don't show it to me in the parent view. And so when you actually run your torch ONNX export, in your export modules as functions, you pass your torch NN class. In this case, we have a class in torch called rotary embedding. We pass it, and all the rotary embedding classes in our model, each instance it shows up, will get translated into an ONNX function when we see the ONNX model. And so that's what it looks like in the parent view. Much simpler to look at. When it comes to pattern matching, we only have to pattern match against the inputs and outputs to our llama rotary embedding function, and we don't have to look at all those nodes that we saw earlier. Another thing that one other thing. So to compare how much simpler it is, when we replace subgraph nodes, this is just an example of the code that kind of is written to do that actual replacement, not even the pattern matching, just the replacement itself. When you replace the subgraph nodes, you can clearly see it's a lot more code than it is replacing an ONNX function. Okay, perfect. And then the other thing I wanted to point out was, so once we do these replacements, we replace, let's say, an ONNX function with an ONNX runtime contrib op. What we'll do is we'll try to optimize the implementation of that contrib op as well. And within the rotary embeddings, we found a way to optimize the caches that I was describing before. So here's an example of how the caches look in Hugging Face for the cosine and the sine caches. Actually, I'm going to pose this as a question. Does anyone see anything peculiar about these caches? There's someone in the online thing, just ask them, yeah. I'll give it like 20 more seconds.
I don't see a question.
Can you repeat the question?
Oh yeah. Do you see anything peculiar about these caches? Specifically the values. Nothing. Okay. Maybe this will help. The left half is identical to the right half in both. Why are the numbers written twice? That's just the way Hugging Face computes them. With an ONNX runtime, we found this, we kind of made this recognition and cut the caches in half accordingly. And when we actually have to do our mathematical operations in the kernel, we just loop over each row twice as needed. Why can we do that? Well, back to kind of simple math again. If you've taken any basic math class, you might know about modular arithmetic. The idea there is you do your integer division, whatever your remainder is, that's what the modulus function kind of produces. So using modular arithmetic, we can kind of go through each row twice and get the right index as needed when we need to extract the specific value. Moving on, another type, and honestly the more common type is attention. Every latest LLM model has attention in it in some form. Between model to model, attention is basically the main thing that changes. There's always a new operator for attention. There's always a new implementation. This is just a small list of the types of attention operators that might show up in a model. Multi-attention, packed attention, sliding window attention, multi-query attention, group query attention. I mean, the list goes on. And then on top of that, there's different algorithms to compute these attentions. There's memory efficient attention, flash attention v2, scale product attention. And that list also goes on. So it can be very exhausting to figure out which pattern corresponds to which operator. So I'm going to kind of take a shot at trying to show that. So this is self-attention. This is kind of the original version of it. You have 4 inputs. You have a query, key, vector, and attention mask. The query, key, and value, the concept kind of comes from search, where you have a query and you're trying to match that to a set of key value pairs. And the attention mask is there to help us make sure any values that we want to see versus any values we don't want to see are set accordingly. So I'm going to try to map what this simplified graph looks like to the equation. So we take our input, we multiply it by some weight vector, we add its bias, we do some reshaping and transposing, and that gets us our query. For key, we do the same thing. It has its own weight and bias, and then we transpose it so that when we want to do the Q times K transpose matrix multiply, we can do so. Then we divide by the square root of dk. D sub k is the number of attention heads. It's basically used to solve the vanishing gradient problem. It's more of an issue with BRAC propagation than it really is an inference. We add our attention mask M, we apply our softmax to get our scores, and we compare that against our values. So this is the value path. And then the final result of that matmul gets you your attention. We do some reshaping and transposing afterwards to make sure it's in the right shape and format in the output. So that's self-attention. Then there's cross-attention. Difference there is in the inputs, they're all separate. So in self-attention, they all came from the same input. In cross-attention, they come from different inputs. So that's a pattern matching problem. Have to kind of navigate that difference. Then there's cross-attention with key value cache. So key value cache is the idea there is once you process your prompt in an LLM, let's say the prompt is 40 tokens, and you're starting to do your token generation. You're generating your 41st token, your 42nd token, your 43rd token. These computations start to become repetitive because they're already been pre-computed for the first 40 tokens. And so when you want to generate your 41st token, you only actually have to do these operations to generate the new query or the new keys and values for that 41st column, and you can reuse the previous 40 columns. So that's the idea here. You have your pass key and your pass value. Your concatenation operation will take the output from these paths that are generating that 41st column, concatenate them together as your present key and present value, and then you can reuse those outputs as your inputs when you want to generate your 42nd token. Then there's cross-tension with the rotary embeddings. The idea with the rotary embeddings, the idea with embeddings in general are that you apply them usually in the beginning of their model. They're usually positional embeddings. LLMs usually require them to gain some specific information about position. And lately, that shift has gone towards rotary embeddings, and the idea there is to project your embeddings into a new space by using rotation matrices that are defined by those cosine and sine caches. So those are also the rotary embedding operators that can show up, and that's why you have rotations on the query and rotations on the key. And so that's what maybe a graph like this would look like, or a graph like that would look like. So in this case, we have our initial input up here, circled in red. And that's going to go to our query and our key matmuls. And we have those rotary embedding options. They're shown here as ONNX functions, as we just talked about before. Then there's the matmul of the two, which is happening right here. The division by the square root of d sub k. The addition of the mask m, applying the softmax, multiplying it by v, which is over here, and that matmul is done over here. And then that's basically your output of attention. And then I'm just circling it here kind of for reference. There's usually an output projection matrix multiply that happens after attention. Those circled operators are really all we care about. Everything else that's in this graph is just computing ancillary stuff that is needed for those actual core operators. So we can remove them. And then in our actual implementation of the, let's say, the multi-head attention operator, we can simplify what the ONNX graph looks like to this. You have your core Q, K, and V matmuls. You have the rotary embedding operators for Q and K. You have your pass keys for key and value, the present keys and values, the multi-head attention operator, and then that output projection node that I was mentioning for reference. Then there can also be cross-attention repeat KV heads. So repeat KV heads are over here and here, and the idea is when you're computing attention, usually with multi-head attention, you do it across multiple attention heads. Sometimes those attention heads, the number can be different in the K and V paths than it would be from the Q path. So the repeat KV path is just to make sure that they're the same by the end of the computations in those paths, so that the core attention computation can be done smoothly. And we noticed that is coming up more and more often, and so we've labeled that as group query attention, as it's more commonly known as in the space. And so this is like an example of the original, in this case, the llama model, and you can see the repeat KV path is here. And so we pulled up the config files that you would see on Hugging Face, for example, for Llama. So this is a 7 billion model. You can see that they're both identical. Same thing for the 13 billion model. But then when you look at the 70 billion model, they're different. If you look at Mistral, for example, another popular model out there, its number of attention heads and its number of key value heads are also different. So these kinds of models, like the 70 billion model, the Mistral model, they need this operator group query attention so that it can support that repeat KV step, essentially. But the nice thing is about the implementation, in our implementation of group query attention, it doesn't matter to us whether the values are identical, like the same, or if they're different. So we've supported both cases. And in our actual fusion, all that happens is we've just replaced that multi-head attention operator with the group query attention operator. And then during that operation, we added some additional things in the kernel. For example, I mentioned briefly there's an algorithm called flash attention v2. It's basically an efficient way of computing attention using tiling. We've integrated that into the support in the kernel computation of group query attention. We've also integrated something called past present share buffering. What that means is when we talked about earlier about those past and present KV caches and how we have to concatenate each time, what it looked like previously in the graph was, okay, you have a separate past input, you have a separate past output. The input might be have the first 40 tokens, the output might have up to the first 41, but they're separate memory allocations. They're not using the same shared memory allocation. So past present share buffering uses the same memory allocation for both the past and the present outputs, or past input and present outputs. And the way to activate that is to just pass the maximum size that these KV caches can take to the group query attention operator, and it'll be enabled for you. There are scenarios where maybe you don't want to do that. Maybe you're in a memory constrained environment and you don't want to, have such large KV caches in memory. Then you can just turn off that feature by specifying the exact size you want for your past and present KV caches, and it won't do the buffer sharing then. So the code that's kind of highlighted here is how you'd actually kind of implement that. So here we're showing like if you want to initialize your past keys and values, if buffer sharing is on, use the max length. Otherwise, start it at 0 because we haven't started inference yet. And then over here, when you do your I/O binding, so I/O binding is used for non-CPU execution providers. The idea is to put your inputs and outputs directly on your target device's memory, let's say like your GPU. So you put it in GPU memory directly. So you don't have any GPU, CPU, CPU to GPU transfers. Those transfers can take up time. And so the idea is you bind your inputs and outputs to your model directly to on-device memory. And in this scenario, we want to bind our outputs directly to our data, our input data's exact reference. So we would use this scenario here where V is like the name, V is the, what did I define V as? Oh, V is the actual tensor. So we access the tensor for the present version rather than the past key value version, and then we can use its data pointer. If we didn't enable past present buffer sharing, we would just use the specific output name and specify that tensor's data pointer accordingly. Okay, so it's great that we've done these optimizations, but models are still large after all these optimizations. So sometimes you have to apply quantization. There's a lot of algorithms for quantization out there, a lot of different precisions. There's int8 precision. There's algorithms in there like smooth quantization, dynamic quantization, int4 precision, which is becoming more popular now. Algorithms like RTN, GPDQ, maybe you've heard of them, maybe you've not. To kind of worry about these different bits and different precisions that people target, we added an operator called mapmul n bits. And what that does is it quantizes the weights within our mapmuls to anywhere between 1 to 7 bits. Your choice how many bits you want to use. And currently it's implemented as a simple operation. When you actually want to do your matrix multiply, you have your input A, your weights B. You want to dequantize your weights from whatever precision you quantized them to back up to whatever precision A is so that you can actually do the mapmul operation. Can't really do mapmul operations in different precisions. And so that's what that looks like here in the graph. You just replace the mapmuls that were there earlier with this mapmul and bits operator. Let's say we use in4 precision, and you actually apply this mapmul and bits quantization technique. You would actually be able to see on disk the file size is cut by however many bits you use. Say in4, it would be cut quite a bit by factor of 4 if, let's say, you're using float 16 precision originally. So it's great that we have all of these quantization and optimization techniques, but let's actually see some numbers. A lot of these models, after we apply all these optimizations and quantizations, look really similar. Very small variations between model to model. So what I've done is I've just taken the Llama 2 model as an example to show, but these optimizations and quantization improvements show up in our performance results for other models like Mistral, Phi2, which is a Microsoft research model that came out. So yeah, let's take a look here. So for prompt processing, we can see that we get up to 2.75 times better than PyTorch. And that's for the 7 billion model. For the 13 billion model, I think it's 4 point, looks like 4.25. It looks like 4.25 times better than PyTorch. And we've also compared against PyTorch Eager and PyTorch Compile. So PyTorch 2.0 released this API called torch.compile to improve its performance. So you can also see the numbers kind of in reference to that. For token generation, which is usually the scenario that people care about more, in terms of speed up, we see up to 1.4x times better than Torch Compile for the 7 billion model, and it can generate up to looks like 1,300, 1,350-ish tokens per second. For larger batch sizes, even for batch size 1, it can generate up to 100 tokens per second for the 7 billion model. For the 13 billion model, we get, let's see, up to 2.0x improvement over PyTorch Compile, and we get, looks like 700 tokens per second for like the max batch sizes, and even for the smaller ones, you can still get around 100 again, 100 tokens per second again. And finally, the end-to-end scenario, probably the most common thing everyone asks. We are up to 3.5x better than PyTorch Eager and Compile for the 7 billion model, and for the 13 billion model, we're up to 4.5x times better than Eager and Compile. So the good thing is about these graphs, if you actually want to look at them more, they're actually already out, publicly available. If you go to onnxruntime.ai, visit our blogs, we have a Llama 2 blog that has these graphs that you're seeing here, so you can check out the numbers and more details on what we did there, if you're interested. So for the end-to-end scenario, how do you actually run this in code? At the moment, sometimes you have to rely on Hugging Face, specifically its optimal package, because when you export, you're just running the forward pass in your model. So you're getting input IDs, which is the output of your tokenizer. The output of the model is logits. Then you need to analyze your logits somehow to decide, what's my next token, what are my next inputs, and then finally, once you have your final outputs from your model, converting that back into actual text. So this is kind of an example of how it integrates easily within Optimum, but it's not ideal, right? If you want to have the greatest benefits and performance benefits from ONNX Runtime, you would want the entire end-to-end scenario to be within the ORT ecosystem. And so that's why the Gen AI API was created. And I believe Ryan will talk about that later today, so I'll leave that part to him. Yeah, so kind of in summary, this is the pipeline that we kind of looked at today. We exported to ONNX, made some improvements in our PyTorch code to improve optimization, applied some of these operators in our graph by detecting subgraphs, removing them and replacing them with those operators that are within ORT, and have implementations that are highly optimized. One thing I may have not mentioned. So when you use group query attention, the flash attention v2 algorithm is implemented in float 16 by default. That's because most of these models are so massive that running in float 32 precision isn't realistic, no matter how big of a machine you really have. So we decided to implement that operator in float 16 precision for performance reasons. And then, of course, the quantization to, let's say, int 4 or int 8 or whatever you pick. And it's great that we have all these optimizations and quantizations, but it can also take a while to run. As a kind of simple example, when we did all these optimizations and quantizations for the Llama 2 7 billion model, it took over an hour. And most of that was in the optimization stage. And so we recognize that, and so we've decided to create some new tools to improve this process. Firstly, you have the transformer optimizer script, which kind of does the automation for you. The Torch Dynamo exporter, so that'll produce ONNX functions by default now. So we saw the benefit of ONNX functions within the rotary embeddings, how you don't have to pattern match against all those nodes, and you just have to pattern match against the inputs and outputs. So the Dynamo exporter is really helpful there for us because it simplifies our pattern matching process and makes us more robust to changes within source code in the future for other models. And then there's something called the ONNX rewriter, which we're working on, which will allow us to convert those ONNX functions to actual ONNX runtime operators that are optimized. We're also working on a new model builder tool. This actually got released, I think, on Wednesday or yesterday. I don't remember the specific day, but it got released this week. And basically, it takes that entire pipeline that you saw and cuts down the amount of time it takes dramatically. So I think I said previously it takes about 1 hour. With the tool, it took 3 minutes, a 20x improvement. So it's a great tool that we have. It is limited, though, right now to Llama 2, Mistral, and Phi 2 at the moment, but we plan to add support for it going forward. It's a brand new effort we just started. And that's actually hosted in the ONNX Runtime Generative AI repo. And as I mentioned earlier, that Gen AI repo is very helpful for having the entire end-to-end solution in the ONNX Runtime ecosystem. And yeah. So all of these efforts are great because it helps us with optimizing, quantizing, running end-to-end inference for a lot of open source SLMs, small language models, and LLMs, large language models. So for some examples, the Llama architecture, so you got Llama, OpenLlama, which was released with Llama, the first version of Llama, because Meta had restricted the weights. CodeLlama, which I believe just recently got released, and a lot of other variations in the Llama model family. Mistral and Zephyr. So Mistral is a model that came out of Mistral AI recently. That's been already fully optimized and quantized if you want. That pipeline's already set up. Zephyr is a fine-tuned version of Mistral, so our efforts for Mistral were easily transferable to Zephyr because our process is only dependent on model architecture and not model weights. So fine-tuning doesn't change necessarily any of these optimization pipelines. The Yi model, which I believe came out of a company in China, I don't remember the name off the top of my head. Falcon similarly came out of a company, I think, in the UAE. And then we have Phi and Orca, which are Microsoft research models that have been released to the public. They are available on Hugging Face if you just search up, like, I think the latest Phi is Phi 2 now, or Orca 2. So we've added those as well. And we support over 10,000 models on Hugging Face that are within this Llama architecture family. Llama is kind of the foundation model, I would say, or maybe even you would say GPT-2 if you're thinking pre-Llama. And yeah, so all those models in that architecture family are already supported. And we have over support for 130,000 models on Hugging Face in general. So it's very likely that the model that you're working on is already supported in this pipeline. Even if it's partially supported, please raise an issue on our GitHub, and we'd be happy to fully support it. Or it'd be even great if you could write some of these fusion patterns and make an open source contribution. So yeah, here are some references if you're interested in learning more. I don't think I linked the specific blog, but if you go to the ONNX Runtime blogs, you can go check out the Llama 2 blog if you're interested in the numbers. And then I don't know if it's been added in the chat because I didn't get a chance to add it in the slide here, but we've already released actually optimized ONNX models for, I believe, Falcon and Mistral on Hugging Face directly. Hopefully someone in that chat can drop the link to it. And yeah, you can also download those, run them, and try them out. Thanks.
any other questions from the chat?
I don't see any questions.
I have a question. So how exactly do you produce?
So I have a question. How exactly do you produce these kernels for these operators? All this fancy attention for this particular pattern. How exactly do you write it? Custom CUDA, Cutlass, by hand?
So a lot of it is CUDA code. Let's say you're writing on a GPU for the CUDA IP. It's a lot of CUDA code. We do have integration with Cutlass as well for our attention kernels. If you're using other EPs like TensorRT, we have their binaries as well with